Hello, everyone. In this video, we're going to go through the solution for example 2. And so we have the skier being pulled up a slope. So the skier has weight. We'll start with the non-contact force. Weight goes straight down. And we can label it as lowercase w or mg or f sub g. Any of those are fine. Just pick one. Stick to it for this problem. What's the skier touching? They're touching the slope, which is creating a normal force. And the slope is also causing friction. And let's see, they're going up the slope. So the friction is going, this is kinetic friction going the opposite direction. Lowercase f subscript k is the standard notation used in your textbook and in these packets. And then there is a tow rope. And so that is up the slope. And that gets capital T. All right, so there's the free body diagram. Now we're going to do a work diagram and calculate the work for each of these. So T, F sub K, F sub N, and weight. And then we have an extra space. So the work diagram, we want to be sure to draw the displacement in the actual direction of the displacement. So that's my displacement. And actually I'll make that my force. We'll do that in blue. Then I'll draw my displacement in red. Okay, so the angle there, 0 degrees. And in this one, displacement is still the same direction, but the friction is this way. And the angle between those, oh, forgot to label it, F, K. And then the angle here is 180 degrees. All right, for the normal force, again, drawing the displacement in the actual direction of the displacement and the normal force in the actual direction of the normal force. And then the angle, 90 degrees. And the weight is going straight down. And the displacement is going like this. And this is the hardest one probably in this problem to get the angle on. But if we look up here, we know that the slope is 30 degrees from horizontal. So if this axis is 30 degrees off of kind of what the standard is, of that being a standard x-axis would be horizontal, we're tilted 30 degrees from that. That means the y-axis is 30 degrees from its typical position as well. So that's 30 degrees, and this is 90. So that means this is a 120 degree angle. All right, so that takes care of all of our work diagrams. Now we can calculate the work done. The work here is 280 newtons times, let's see, 50 meters times cosine of 0. And cosine of 0 degrees is just 1. So 280 times 50. You can type times cosine of 0 into your calculator if you want, but it's not going to make any difference. We have newtons times meters, and that's 14,000 joules. And we could put some subscripts in here. Let's see, the friction is 35 newtons times 50 meters times the cosine of 180 degrees. It's important to get the angles from your work diagram and not just from the problem description. So 35 times 50 times cosine of 180, which I know is just -1. So that comes out to -1,750 joules. Work done by the normal force is equal to the normal force times 50 times the cosine of 90, and this is 0. Okay, so here I crossed it out and wrote a 1. Here I'm crossing it out and writing a 0 because I know the cosine of 90 is 0, so I don't need to bother to find how big the normal force is. I know that some number times 50 times 0 is 0. And this is the work done by the weight. So let's see, the weight is 50 kilograms times 9.8. Okay, that part is the weight. And then times 50 meters times the cosine of 120 degrees. So this is going to be a negative value. 50 times 9.8 times 50. There's two 50s, the kilograms for the mass, and then the displacement, magnitude of displacement, times cosine of 120. And that comes out to be negative 12,250 newtons. Oh, joules. Sorry about that. Joules. This is newtons. Newtons times meters is a joule. And now we add them all up. So we'll just use this space here to add them. 14,000 minus 1750 plus 0 minus 12,250. All right, so 14,000 minus 1750 plus 0 minus 12,250. And that comes out to 0. Oh, sorry. There you go. Now you can see. That comes out to 0. That might seem surprising at first, but we were finding the total work done by all the forces, not just the non-conservative ones, but all of the forces. And since the object was moving at a constant speed, it actually does make sense that the total work done by all the forces is 0. All right, if you have any questions, please consult your instructor.